In this video, I will present some project results. We choose the paper Adversarial Skill Networks because it presents a label-free robot skill embedding. The learned embedding are transferable real-world robot tasks and can be evaluated using synthetic and real-world data sets. And finally, the code and the data sets are publicly available. Let's briefly summarize the paper. This paper is for dealing with the problem that most deep reinforcement learning methods typically learn solutions from scratch for every task and often rely on linear, and do not transfer to new tasks in general because its policies and representations are task-specified, which means that this approach is not only inefficient, but also limits the versatility and adaptivity of the systems that can be built. Then in a typical robot learning task, each agent behavior is often treated as a discrete action. However, in reality, tasks and skills are continuously learned like humans. Therefore, the concept of continuum of skills was introduced. ASN introduced in selected paper proposed on unsupervised skill learning framework from video input. The learned embedding from ASN can be then transferred to learning on scene skill by an RL agent. First one is related to time contrastive network. Even though supervised learning has been successful on a range of tasks where labels can be easily specified by humans, it will be impractical to label every aspect of boarding task in enough detail to allow a robot to understand all the task relevant properties. Therefore, this paper addressed these challenges by using a self-supervision and multi-viewpoint representation learning. Second thing, introduced extended TCN called MFTCN that encodes temporary latent states such as velocity, angular velocity, acceleration, by allowing it to embed multiple frames jointly. They show that a new approach for robots to teach themselves about the world simply by observing. In particular, they investigate the effectiveness of learning task agnostic representations for continuous control systems. Last but not least, because generative adversarial networks GANs are not optimal on discriminative tasks and can be limited to simulation. This paper proposed a unified framework for adversarial domain adaptation, allowing users to effectively examine the different factors of variation between the exciting approaches and clearly view the similarities they each share.
In the original paper, there are two different data sets. The first one is simulated data sets and using pipeline setups, and the second one is real-world data sets. In the real-world data sets, ASN used simulated data sets of task A, B, and C, and demonstrations using a different task B. Using aforementioned data sets, ASN trained how to embed different views of skills in contrastive manner. As you can see here, there are encoder network loss and discriminator loss for embedding skills from demonstration videos. Here are details for the applications. You may pause the videos to read this. To evaluate ASN's embedding performance, we use two different metrics. The first one is alignment loss, which represents difference between ground truth time and KNN align time. And the second one is distance between positive and negative embedding. Based on aforementioned metrics, we measure ASN performance. As you can see here, we could observe that the ASN can effectively disentangle negative and positive pairs as training progresses. Based on pre-trained embedding networks, author conducted control policy learning experiments. The proposed method succeeds in serving the task, whereas the baseline TCN approach converges to a local minimum. Unfortunately, the author didn't release the synthetic data sets and RL experiments. Therefore, we investigated the experiment as similar as possible to the experiment conducted in the paper. We find similar setups of both PandaGym. Based on PandaGym experiments, we trained expert agents using PPO algorithms for each task. Using expert agents, we can train agent by imitation learning method. As you can see here, expert agent can generate demonstration videos. Based on the demonstration, we can train student agent by using behavior planning algorithm. There are several limitations in our control policy application due to the recent library updates. Therefore, we will discuss how we handle these issues in the next section.
So we came up with three different modification approaches. First, fine-tuning the network using our synthetic appendage environment dataset. Second, modifying the discriminated network objective by aligning embeddings in a more symmetrical approach and introducing Wasserstein distance loss. And third, introducing encoder network objective uh, using the Wasserstein distance, triplet contrastive loss, and contrastive loss between positive and negative pair in Bay. On the right, you see 9 different experiments that we conducted, and we'll discuss this in the later slides. First, in order to generate our synthetic data set, we came up with 6 different pairs of camera parameters. So, for the yaw, pitch, and roll, as you see on the right, yaw, pitch, and roll are shown um, as in the figure. And using these parameters, we generated 6 sets of 2,000 images per view, and each view is shown on the figures below. And second, in the discriminator, we aligned embeddings in a more symmetrical approach by introducing Jensen-Shannon divergence instead of Kullback-Leibler divergence. And second, we introduced Wasserstein distance loss instead of KL divergence. And yeah. And third, we also modify the ASN encoder network objective by introducing self-supervised contrastive loss and also Wasserstein distance loss. We introduced Wasserstein distance loss because Wasserstein metric is a true probability metric that provides meaningful and smooth representation of the distance between distributions. And as final goals, we seek to obtain a better domain adaptive embedding learning network by acquiring embeddings that better suited to the trained data domain and applying the network to a different task. And second, we hope to integrate the learned ASN network into the imitation learning environment using the PPO algorithm for the expert agent and using the behavioral cloning algorithm for imitation learning. And we add our modifications to the ASN and imitation learning to acquire better performance. And the experiment results. The experiment implementation details are shown on the page. We use these libraries and versions for all the experiments. And first, applying ASN to RL, we first formulate as ASN formulates this distance metric as the reverse signal for the task. We directly applied this to the RL setup, and our experiment consists of 3 different stages. First, we train the network on a stacking colored block task, and as shown previously. And second, we pre-train an expert agent on an unseen task using the PPO algorithm. And third, we trained a student agent according to the imitation learning algorithm. And so, as ASN changed the encoder here, we hope to learn better embeddings by our modifications and achieve better reward as in the RL setup. In stage 1, we first fine-tuned ASN to our synthetic data set, and we used the ASN network pre-trained on the synthetic data set that is not released to the public. And you just see on the our training graphs, we see the distance between positive and negative increases over iterations. However, the network distinguishes between each video is worse than before fine-tuning. And similarly, we pre-trained ASN on our synthetic data set, and we observed similar results. And we report the validation results on our synthetic data set. And we observe that fine-tuning to our synthetic data set results in lower alignment loss and higher distance for all few pairs of the same frame, and the higher average KNN distance. And among the three experiments that involved our synthetic data set, we saw the fine-tuning the real data set pre-trained model to our synthetic data set resulted in the highest distance metrics. In stage 2, we originally thought to train our expert PPO agent on the panda push task, but we modified our plan to train on the cart pull task due to the consistent errors that we saw before. And in stage 3, we trained an agent according to imitation learning, specifically the behavioral cloning algorithm. And as you see on the graph here, compared to the experiment 4, which is training only on our synthetic data set, the contrastive loss replacement in the encoder network objective led to the maximum reward at smaller iteration steps. And we trained the RL according to the distance metric as presented in the ASN network on the right here. Here's the conclusion. We did fine-tuning on our synthetic data set, further widen the distance between positive and negative samples during training, despite slightly worse distinguished power in the embedding space. And modification to the encoder and discriminator networks in the ASN lead to a smaller number of iterations required to reach the maximum desired reward. And the simple limitation learning approach performed relatively well in small amounts of required time and space. And the limitations of our work is that we verify the performance on the same domain task after fine-tuning and optimize the network and other hyperparameters for superior performance. A natural extension of this work is the application of the learned distance metric in a real-time reinforcement learning setting, such as simulating tasks in virtual environments and imitating the task policy in the real-world robot control. We can also combine language guide to imitation learning to enable a robot to learn perceptual and linguistic understanding, together with task agnostic control in an end-to-end manner. Thank you for your listening.